we are going to add layers in the model which is already provided. So we are importing all these libraries, and we have to create encoding and decoding layer model from for the MNIST data which has been provided, and this data we can get it from the keras. So for this ICP, the model is already provided, and we have to add additional layers into the encoding and decoding model so that it can be improved or not, or it's not necessary it will be improved, but the main idea is like we have to implement this model, and also we have to add additional layers into the model. So here we are loading the data into the training and test, and basically we have 60,000 of data in the training, and all the image we have into the 28 by 28 size. So for simplification of the model so that we can work on it, so we have taken only the 10,000 of the image, and this is the first 10 image from the data. So it's like we can see it, and we have to develop a model which can predict this image through the encoding and decoding. So we have taken the 10,000 of the model, 10,000 of the data, and each image has a 28 by 28 size. So 28 is the width and 28 is the height. So here we have given the specification for the data in the model configuration. So we have a width 28, height 28, batch size is 128, and number of epochs we have given as a 50. So validation split for the fitting of the data do after creating a model is 0.2. It means 20% of the data will be used for the testing. Verbosity we have set as a 1 so that we can see how the loss and accuracy is being changed. Latency dimension is 2, and the number of channels is 1 because this is the grayscale, so we are not considering it as a RGB, so we have only one channel, that is 1. So here we are reshaping the data and we are normalizing the data. So we have the pixel size of the each image ranging from 0 to 25. So we are dividing the data by 25 so that it will be normalized. And this is the basic definition of the encoding def model. So this is what we which has been provided in our ICP. So I can show you what we have changed. So this is the replica of the same thing. I can tell you where we have the change. So here put the filter size of the so in our previous model we had just the filter of 8 and 16, that is the conventional to do 2D uh, layers. So we added the 32 and 64 here with the kernel size of 3 and 3. This is the encoder definition, and I've removed the strides is equal to 2 here because the number of size of the image was not intact. It was coming below the like uh, what we were expecting. So we put the kernel size is equal to 3 and the filter size equal to 32 and 64. So these two layers were added into the encoder, and going down we found the conventional shape as a 7, 7 and 32. Like this will be the input for the decoder. Here we are calculating the mesh dimension and epsilon value for the model, and this is our the encoder shape or encoder summary of the model, like how it's working. So see, after 28 size, the size of the shape is changing from 14 to 7. So this is our encoder model summary. Then into the decoder summary, what I have added, it's the same thing but in the reverse order. So we added one convolutional 2D transpose with the filter size of 64 and again with the 32, the same way which we did into the encoder, in which we have added 32 first then 64, and we also added the best normalization between them. So this is what we have added into the decoder definition. And after adding this is our the model for the decoder. We are getting as output as 28 by 28 into 1. So this is what we wanted, like the shape should be in the 28 into 28 into 1. Then we have combined both decoder and encoder, and this is like VAE outputs which we have. So the encoder input will be 28 28 1. 1 is number of channels, 28 is like the height of the image, 28 second 28 is like the width of the uh, first one is the width, second one is the height, and the same should be the input for the decoder. Then we are compiling it here and the training it. So after training we have found, like in our initial model we were getting 0.1966 loss. So here we have 0.1897, so we have an improvement on the loss. And here we have visualized the data, so there is an improvement if you'll see. So if you want to see the data and if you want to compare with our previous model, so this is our previous model. So if we'll see and if we'll compare, so there is a lot of improvement after adding these two models. So this is the part of ICP which we have done. Thank you.